So let's continue with our discussion and let's solve some problems to begin with. We have the problem set for discussion on motion of symmetric top, or rather motion of systems. At first we start with an identity. Consider torque free motion of a rigid body with one point fixed, which we are doing in general, and torque free means n is equal to 0. Uniform rotation is defined when dl dt is equal to 0. Show that the uniform rotation about an body axis is dynamically possible if and only if that axis coincides with one of the principal axis of the body. So, what is the statement of the problem? The statement of the problem is, okay, please first recall that dl dt is different. The expression for dl dt depends on whether we measure it along the space set of axis or the body set of axis, and we can write the equation dl dt space is equal to dl dt body plus omega cross L, which is equal to n external. That is when one point of the rigid body is fixed and it is executing a rotational motion around that particular point. Now, in our problem, n external is equal to 0. So, if n external is equal to 0, then this whole thing is equal to 0, right? And we have already seen that from the space set of axis, dl dt space is equal to 0, which implies L is equal to 0, which this we have already seen. Now, what happens in body set of axis is dl dt plus omega cross L becomes 0, which implies, so we should write dl dt body. So, dl dt body is equal to L cross omega. Now, when we are discussing uniform rotation, that means, so uniform rotation around body axis will mean that dl dt body will also be equal to 0, right? Because that is the definition of uniform rotation. When we are measuring from space set of axis, then we are setting dl dt space equal to 0. When we are measuring from body set of axis, with respect to body set of axis, when we are discussing the motion with respect to body set of axis, we set dl dt body equal to 0. Okay. Now, if we do that, we see from this equation that dl dt equal to body is equal to 0 implies L cross omega is also equal to 0, and this implies L parallel to omega. So, we see that for torque free motion, uniform rotation is possible if and only if L and omega remains parallel, and from the relation we already know that L is equal to I tensor times omega, and only along a principal set of axis. If we resolve it around a principal set of axis, what do we get? We get I1, I2, I3, omega 1, omega 2, omega 3. Okay. So, this will give you around a principal set of axis L equal to I1 omega 1 x cap plus I2 omega 2 y cap plus I3 omega 3 z cap, right? Now, if L is parallel to omega, that is possible if and only if omega is omega I xi cap. So, omega has to be, or the axis of rotation has to be one of these. If we have a general direction where all three components are present, then these two vectors omega and L and omega will never be collinear, never be parallel to each other. Only if omega is given, omega is defined along one of the principal axis, then the other two terms, for example, if omega is equal to, omega is equal to omega 1 x cap, that is it, and then these two terms in the expression vanishes, the second and the third term, then L is simply I1 omega 1 x cap. So that means L and omega, they are collinear to each other, and this condition is met, and we have uniform rotation from this as described in the problem. So I think this is clear from this set of calculation, or set of it is not exactly calculation, but set of consideration, that only if we are describing rotation around a principal set of axes, then we can have uniform rotation for measure. Please remember, we are talking about body set of axes. So uniform rotation around body set of axes is possible if and only if we are describing the rotation around one of the principal axes. So this theorem is, this identity is something which we are going to understand little bit more details in details when we are doing our next problem. So the next problem is a problem of rectangular lamina. Rectangular lamina which has sides A and B, which is shown in the figure, and it lies in the xy plane. Now in this plane, we define an axis of rotation which runs through the axis of or through the diagonal of this lamina. And so first we have to find out a moment of inertia which along this particular axis of rotation. Secondly, we have to find out the angular velocity or angular momentum L around this axis of rotation, and thirdly we have to calculate the torque which is required for this to maintain this uniform rotation around this axis, and finally we have to take A equal to B and see what happens to all this quantity. Okay. So this was our problem 1, where we proved where we got a condition for uniform rotation. Next we have problem 2. Now for problem 2 we have our axis system, and this is my lamina. Okay, so we have x, we have y, and the sides are given by A and B, and this is my n capped, right? So n capped is given as, so the diagonal vector when we have A and B is simply bx cap divided by root over a square plus v square, a y capped divided by root over a square plus v square, and 0. So if you take the magnitude of this, you will see magnitude and direction. If you consider it carefully, you will see that it has a magnitude of 1 and the direction given in this axis. And then we have the and from the symmetry of the problem, we know that we understand that x and y and the z axis, which is perpendicular to both x and y. So basically pointing out of this plane of paper, these are the principal axis of the system. That is from the symmetry of the problem. There is no mathematics needed, and I can tell you that Ixx, which will be one of the principal moment of inertia, is 1 by 12 m b square, okay, which is the mass of m being the mass of this one. Yeah, so this will be b square. Iyy will be 1 by 12 m s square, and Izz will be 1 by 12. From the perpendicular axis theorem, it will be m s square plus b square. So if I give you this one and this one, the third one is obvious from the perpendicular axis theorem, right? So I am giving it to you to begin with. You can always calculate this. It is very easy. You can find how to calculate Ixx and Iyy in any of the textbooks. Now let's look into the first part of the problem. First we have to calculate I, which we know is a projection of the total moment of inertia tensor around this particular direction. Okay, so it turned out that this projection, in order to calculate this projection, what we can do is we can take out a square by root over a square by b square, m by 12 common. So it will be m by 12 a square plus b square to the power half common, and inside we have b a 0, b square a square plus b square b a 0, right. So if this is the case, then 12 a square plus b square to the power half. Now you see this one, it will give you b cubed, a cubed, 0. So it will finally, the result will be b to the power 4 plus a to the power 4. Sorry, it's, yeah, that's it. So this is the result. So that's answer to part 1. Now answer to part 2 is where we have to find out L. Okay, and we know that L is equal to I tensor times omega once again. So sorry, so once again I is given by this tensor multiplied by m by 12 prefactor, right, and omega is given by this vector multiplied by this prefactor. So, oh sorry, actually there is a mistake. So because n is coming twice in this expression, so this to the power half will vanish and we will have simply this, right. Now for this one it will be m by 12 a square plus b square. Now this half will survive because this is nothing but I omega n capped, and there will be a omega coming up here, okay, this omega, and we have b square a square plus b square, and for n we write simply b a 0, right. So this will give you m omega by 12 a square plus b square to the power half b cubed x cap plus a cubed y cap. So this is the direction of L. Of course we see that L lie in the xy plane, there is no z component, okay, there is no z component at present, that is so actually this will give you a vector. I am just writing it as per the component because it's a 3 cross 3 matrix, it's a 3 cross 1 matrix, it will give you a 3 cross 1 matrix. I am just, instead of writing it, I am just putting it into vector notation, okay. So it's b cube x cap plus a cubed y cap, right. Now third part we have to write out the Euler's equations, and so let's go back to the problem once. So the third part is we have to use Euler's equation and find out the torque required for this rotation, this particular rotation about the diagonal. Now we have already written in the previous lecture, we already written the general form of Euler's equation. I am not, I just don't want to write this. So let's look at this for a while before writing anything. Of course these equations are okay, so let's do it because this is for torque free. So it will be I1 omega 1 dot is equal to just give me a second, I don't recall these equations exactly, so I just need to go to the relevant page of my notes, right, minus omega 1 or omega 2 omega 3 I2 minus I3 equal to N1. Similarly we will have I2 omega 2 dot minus omega 2 omega 3 I3 minus I1 equal to N2. Well, there could be some sign problem. You can check that out. Omega 1 omega 2 I2 minus I1 equal to N3, right? Sorry, it will be I1 minus I2, no, not I2 minus I1, I3 I2 3, yeah, so it will be I1 minus I2, right? Now it is an uniform rotation, so the rotation we have is omega equal to omega n capped, and omega is a constant. So if it is an uniform rotation, these three equation, all these three terms immediately vanish. All these three are uniformly equal to 0 because omega is an uniform rotation. And we see n only has a and b components, sorry, x and y components. So there is no z component of n. So omega 1 is equal to b by what was it? B by a square root over a square plus b square. Omega 2 is equal to a by root over a square plus b square, and omega 3 is equal to 0. So if omega 3 is equal to 0, then if we put it here in this equation, so this term also vanish, this term also vanish. So without solving anything, just by looking at it carefully, we see that these three term vanish, these two vanish. So we get n1 equal to n2 equal to 0. So only remaining equation is n3, right? So for n3, we just have to write out the expression for n3, which is by putting the values of omega 1 and omega 2, which is ab divided by a square plus b square, and so there is a minus sign here, it will be I2 minus I1, and if you, so in this case I2 minus I1 is Iyy minus Ixx. So if you put the values ab m by 12 a square plus b square, it will be a square minus b square. Okay. Okay. Oh, I know. So I made a mistake initially. Sorry, where is it? Right. Oh, okay. I made a mistake. So Ixx will be, oh, okay. Ixx will be a cubed actually. Sorry, ms square. Yeah, this makes sense because it will depend on the mass distribution around x-axis, not along x-axis. So it will be a square and this will be b square. Oh, okay. So all this, it will be a square and b square. So instead of this, it will be a square b plus a b square. Yeah, dimension remains same, only some change. So also for the expression of omega, it will be, or expression of L, it will be a square here and b square here. So it will be a square b, right? So it will be a square b and a b square, right? So this is the expression for L. Omega, okay, and for the last part, this will be b square minus a square, because otherwise the torque becomes negative, right? So which is not possible. So it will be b square minus a square here, right? So initially I wrote, instead of by mistake I mixed up a and b. Okay, so our final expression for n3 is this a times b m by this term b square minus a square. So we solved all of it. Now let's go to the fourth part. Fourth part is really interesting because in fourth part it says, now set a equal to b and examine the value of L, omega and n, and you should find L and omega to be collinear and n equal to 0, right? So this is very obvious actually when we look back to the expression. So n is nothing but n3 z capped, so the torque is entirely along the z direction. Okay, but please remember this z is the body z axis. So if for example, if this is our lamina, okay, so let's say if this is the lamina in question, this book, okay, so if this is the lamina in question, it is moving along the diagonal like this. Okay, so if the z axis, which is pointing upward through the center of the book, okay, so that axis itself is rotating with the z axis. So do not think that the z which we are talking about, the torque which we are talking about, is fixed in space. The torque is also varying, changing continuously the direction of it, okay, because this z is the body z axis. But whatever, we can get an expression for the torque v square, okay, and this is z cap. Now fourth part, we set a equal to b, sorry, not vectors, a equal to b. What we see, put a equal to b here, you get n equal to n3 z cap, which will be equal to 0. Okay. Now what happens to L and omega? So let's examine omega. In the expression of omega which is given here, okay, if you put a equal to b, you see the first term will be a square plus s square, second term is also denoted, and a is equal to b. So your after cancellation, your omega will be omega n capped, which will be omega by root 2 x capped plus y capped, right? And what happens to your L? Of course, we have an expression for L. Okay, so this is, so I'll write out the final expression here. Okay, so you set a equal to b, this will be a cubed and a cubed, so 2a cubed, this will be 2a squared to the power half. So finally we have m by 12 a root 2, okay, and here we will have 2a cubed, and the direction will be simply x cap plus y cap, which will after cancellation, so it will be 6 m by 6 root 2, and this will be a square x capped plus y capped. So we see L is parallel to omega, both are in the direction of x cap plus y cap. So initially when we had rectangular, we started with a rectangular lamina. This is the axis of rotation, and it is rotating with an angular velocity omega around this particular axis. Okay, so the angular momentum at that time was not exactly coinciding with, this is the origin by the way, it's not exactly coinciding with omega, staying close to omega, but actually omega was not, I mean, it's not an uniform rotation, so omega will not be constant even from the space set of axis. So it was somewhere around here, which was again, if we have not calculated it from the space set of axis, so I cannot comment how it was rotating at present, but it was not coinciding with omega, right? Now from here, when we move to a case when we have a square plate, then L and omega, they follow the same direction, and the torque required for this rotation vanishes. So if we compare it with the result we got in our previous identity, this is the situation of uniform rotation of a rigid body. Now omega equal to L, that means, that essentially means dl dt around this particular set of body set of axis, which is the diagonal. We will just write dl dt diagonal, just to make it distinguished from any other dl dt body, is equal to 0. Okay. So, this, what does it mean? What does it physically signify? It physically signifies a situation where the motion, the axis of rotation, is one of the principal axis. That is exactly what we have learned in the identity. We started off the class with an identity. In that identity, it was said that uniform rotation about a body set of axis for the torque free case. Please understand that as we set A equal to B, the torque vanishes. So, the torque is also driven by the symmetry of the system. Uniform rotation, to maintain the uniform rotation, we needed torque only when the sides, sides A and this is B and this is A, when A is not equal to B. At moment we have both the sides as A and A, the torque requirement is also vanishing, and that all that indicates that the diagonal also becomes a principal axis of rotation. And it turned out it becomes a principal axis of rotation for a square plate. Now, what happens for a square plate? For a square plate, the symmetry becomes fourfold. When we have a rectangular plate of side A and B, we have a twofold symmetry. That means, if we start rotating it around this z axis which is pointing upward, so at 180 degree it coincides with itself. So, in other word, in a total rotation of 360 degree, it coincides with its own image or own shape only twice. But for a square plate, the symmetry becomes 4. That means, if you rotate it by 90 degree, 90 degree, 90 degree and 90 degree, each 90 degree rotation it will coincide with itself. So, in language of group theory, this is the C4 symmetry point group and this is C2 point group symmetry, but that is not terribly important to understand this. What is important is, when you have a fourfold symmetry of the system in the xy plane, there has to be two sets of principal axis present, two sets of symmetry axis present, otherwise you cannot have fourfold symmetry. And these two sets of symmetry axis, one is of course this x and y, and the other one is just the axis running through the diagonal. So, you can have either x and this, okay, rather let us call it x t, x diagonal and y diagonal. Either you can take this as your symmetry axis or you can take this as your symmetry axis, both will solve the purpose. And this is why, because the axis of rotation is a symmetry axis, we have the torque vanishing, sorry, not this, where is it? Yeah, here. We have the torque vanishing, n becomes equal to 0 and omega is collinear to L. Okay. Fine. So, I think we gain a better understanding of the situation by gain a better understanding of the first theorem or first identity we proved by solving the second problem. We quickly look at problem number 3 before we close this lecture. So, it is a tennis racket which is spinning. Okay. Now, with an angle which is very close to 0, right? We have to comment whether this rotation will be a stable rotation or not. We have seen just now, we have seen for the, or in the previous lecture we have seen the condition for stability of an asymmetric top. We can treat this as an asymmetric top. So, this is not a problem exactly, in a sense you do not have to calculate anything. Just by physical argument you have to comment whether this axis of rotation, which is along the length of the tennis racket, whether it is a axis with highest or lowest angular momentum or moment of inertia. So, let us quickly look into it. Problem number 3. Let us assume for a second that the tennis racket, which, okay, my drawing of tennis racket is not very inspiring, I know. Let us assume that it is a solid object and you set the axis, this is your z, this is your x and this is your y. Okay. Now, let us for a second assume that this is my object. Okay, it's not exactly a tennis racket, but if I make a cut like this on this solid book, it will be a tennis racket. For Z, the rotation about Z is like this. Okay, rotation about X, which is pointing towards U, let's say, is like this, and the rotation about Y, which is pointing towards the line here, is like this. Now, looking at the mass distribution around these three axes, see Z axis, around Z axis, see moment of inertia I is a function of mass distribution, if for a given axis is a function of mass distribution. From the symmetry itself, I can see that around Z the mass distribution is minimal. Around X and Y we have substantial, I mean the distance, average distance from a mass point, what is I? I is sum over I mi di square. Okay. So, if a mass is located far away from a particular axis, for that axis I will gain more moment of inertia. So, for Z axis the average distance of mass points on this system is less compared to any other two axes. So, we can just by symmetry of the problem, I can say that Izz is less than both Ixx and Iyy. So, this is the axis of lowest moment of inertia, and we have seen from our discussion of symmetric asymmetric top that if such a rotation takes place when a spin or rotation takes place in an axis which is an axis of lowest moment of inertia. Now, in this case it is not exactly coinciding with Z, but the angle is vanishingly small. So, we can very well assume that the moment of inertia is around that particular axis which is described here. It is pretty much the Izz, and we can say from the symmetry criteria that this is the lowest axis. So, the oscillation will be, or the on the rotation will be stable. Okay. So, we close this lecture here, and in next lecture we will continue with the discussion of rigid body dynamics. We will be describing something called the Euler's angle.